In previous tutorials, you've differentiated from first principles functions such as c, x, 2x, x to the power n, where n is any power, sine x, cosine x, e to the power x, and log to the base e of x. Now, what we're going to do in this tutorial is to construct a table of these standard derivatives. And when we've done that, we'll look at some variations of those standard derivatives and add those to our table. So let's start with our function, f of x, and our derivative, which may be referred to as df by dx or f dashed of x. So let's start with c. Well, c is a constant, it's a straight line, and it's horizontal, so our gradient function is 0. X, the derivative of x, is 1. 2x, the derivative is 2. If we have x to the power n, then the derivative is n times x to the power of n minus 1, where n is a real number. Sin x, the derivative is cos x. And cos x, the derivative is minus sin x. E to the power x, that's the one that stays the same, e to the power x, and log to the base e of x, where the derivative is 1 over x. Let's look now at a variation of some of these. We'll come back to the table in just a minute. Okay, what if we have f of x equals, instead of just sine x, we have 2 sine x. Well, this is just the same as taking sine x and taking 2 of them. So when we find the derivative, we actually find the derivative of sine x and take 2 of those. Well, the derivative of sine x is cos x, so the derivative of 2 sine x is 2 cos x. Similarly, if we take f of x is minus 5 sine x, then our derivative, f dashed x, is minus 5 cos x. And this, in fact, is the case for any constant multiplied by the function. So if we have f of x equals c times sine x, then f dashed of x is going to be c times cos x. And this is called the constant multiplier rule. So if we have c times our function of x, and we want to differentiate it, so we want to find the derivative with respect to x, it's actually just c times the derivative, df dx, or c times our f dashed of x. Now let's prove this from first principles. If we take our function of x to be g of x, and it's equal to some constant times f of x. Now our definition of our derivative is g dashed x equals the limit as delta x approaches 0 of g of x plus delta x minus g of x, all divided by delta x, which equals, again, our limit as delta x approaches 0. And in this case, our g of x plus delta x is c of f of x plus delta x. So we substitute that in. Minus our g of x, which is c f of x, all divided by delta x. And here I'm going to take the c outside a bracket, so we have the limit as delta x approaches 0 of c, and then our function of x plus delta x, take away our function of x divided by delta x. And because our constant is nothing whatsoever to do with our limit as delta x approaches 0, we can actually take the constant outside of the limiting sign. So the limit delta x approaches 0, and we have f of x plus delta x minus our function of x divided by delta x. So this is c, and this is our derivative. So it's actually our f dashed of x. So our g dashed of x, our derivative, is equal to c times our f dashed of x. Now let's have a look at what we're going to do when we have two functions that are added together. So let's say we have f of x plus g of x, and we want to differentiate them with respect to x. So we want the derivative of that function with respect to x. Well, quite simply what we do is we differentiate each part separately and add them together. So that's the same as df dx plus dg dx. Similarly, what happens if we want two functions that are subtracted and we want to differentiate those? Well, again, the derivative of those functions subtracted is very straightforward, because what we've got here is just the same as we've got here, but with this second function multiplied by -1. And there we're using the constant multiplier rule. So this is just the same as the derivative of d of x of f of x plus -1 times the derivative of g of x. So that's our df dx plus our -1 times our derivative there, which is plus -1 times dg dx, which is just the same as df dx minus dg dx. Let's just return to our table and we can write those in. So we have our constant multiplier rule, c times our function of x is c times df dx. And if we have f of x plus g of x, our derivative is df dx plus dg dx. And if they're subtracted, f of x minus g of x, then the derivative is df dx minus dg dx. Now let's have a look at an example. 2x cubed minus 6 cos x. And we want to find the derivative with respect to x. And that equals the derivative of 2x cubed with respect to x minus the derivative of 6 cos x with respect to x. Now what we have here is the 2, which is, we can use the constant multiplier rule, so that we've got actually twice the derivative of x cubed with respect to x, minus, and again here, using the constant multiplier rule, we can take the 6 outside. So it's 6 times the derivative of cos x with respect to x. So we have twice. Now the derivative of x cubed with respect to x is 3x squared minus 6 times the derivative of cos x, which is minus sin x. So we have 2 3's, 6, x squared, minus times a minus is positive, times 6 sin x. Let's look now at extending the table further. So let's start with our function f of x again, and our derivative df dx, or f dashed of x. And this time, let's look at sine of mx, where m is any constant number, and the cos of mx. Then we'll have a look at e to the power of mx, and then log to the base e of mx. Let's look then at y equals sine mx. Now here we're going to do a substitution, and instead of mx we're going to write u is equal to mx. So therefore our y is equal to sine u. And we're going to differentiate u with respect to x. So du by dx is equal to m. And then we're going to differentiate y with respect to u. So dy by du equals the derivative of sine u, which is cos u. Now, dy by dx, and you'll learn this in the future, dy by dx is equal to dy by du multiplied by du by dx. Now, this is called differentiating a function of a function, or differentiating using the chain rule. And it's the subject of another tutorial. So we're not going to go through the details of that now. What I want you to do is just use it as a formula. Let's now substitute then. Dy by du is equal to cos u, multiplied by du by dx, which equals m. Now we usually write the constant first, so it'll be m times the cos of u, but we introduce the u, and we want actually dy in terms of dx, in terms of x, dy by dx. So what we need to do is to substitute back, and instead of writing u, we want to write mx. So we have our dy by dx equals m times the cos of mx. So in effect, what's happened when we found the derivative is we've multiplied by m. So let's go back and pop that in our table. The derivative of sine mx is m cos mx, and in a similar way, the derivative of cos mx will be minus m sine mx. Again, just like multiplying by the m. Let's look now at e to the power of mx. So our y equals e to the power of mx. Again, we're going to do a substitution and let u equal mx, so that our y is equal to e to the power u. Again, we're going to differentiate u with respect to x, and we get m, and we'll differentiate y with respect to u, and we get e to the u. Our dy by dx is equal to dy by du multiplied by du by dx, And if we substitute in dy by du is e to the u, du by dx is m. Again, let's write our constant terms first. So we get m e to the power u. Now we need to substitute back for our u. So we get m e to the power of mx. So again, our derivative, we've ended up multiplying by m. Let's put that back in our table. So e to the power of mx, the derivative is m e to the power of mx. Let's look now at log to the base e of mx. So y equals log to the base e of mx. Same process again. Let's let u equal mx. So our y equals log to the base e of u. Our du by dx equals m. dy by du, the differential of log to the base e of u, is 1 over u. So our dy by dx equals dy by du multiplied by du by dx. Our dy by du is 1 over u. Our du by dx is m. So we have m divided by u, which is mx. And very conveniently here, our m's cancel out, and we end up with 1 over x. So dy by dx is equal to 1 over x. So let's put that now in our table. So log to the base e of mx is our function, so our derivative is 1 over x. And of course, this is only the case where m is greater than 0, since we can't take the logarithm of a negative number. Let's just go back to the calculation that we've just done, because there is another way that we could have looked at differentiating y equals log to the base e of mx, and that was by using the laws of logarithms. What we could have done was said that y equals log to the base e of m plus log to the base e of x, and then differentiated them. So our dy by dx was equal to, well, log to the base e of m is just a constant. So when we differentiate that, we get 0, plus log to the base e of x, well, we know the derivative is 1 over x. So we end up with just the same as before. Dy by dx is equal to 1 over x. Now, one final one to have a look at is log to the base e of ax plus b. So let's just have a look at that one. So y equals log to the base e of ax plus b. Again, we're going to use the substitution u equals ax plus b. So our y is equal to log to the base e of u. We differentiate u with respect to x. Du by dx equals a. And our dy by du equals 1 over u. Again, our dy by dx is equal to dy by du multiplied by du by dx. Dy by du is 1 over u multiplied by du by dx, which is a. So we have a divided by our u, which is ax plus b. So dy by dx is equal to a divided by ax plus b. So finally, let's add that to our table. The derivative of log to the base e of ax plus b is a divided by ax plus b.